Hello, I am following along with Paul McWhorter's Raspberry Pi Pico W lessons, and I wanted to show off my solution to lesson number 3, understanding and using binary numbers. Big goal with this solution was to avoid statically defining what each number looks like as far as like pin state is concerned. So I didn't want to have a list that said 0 is represented by pin 1, 2, 3, and 4 being off. 1 is represented by pin 1 being on, 2, 3, and 4 being off. Because once you get to like 32 bits, that's 2,100,000,000 different numbers. So you would have to write that many times 4. Well, not times 4. Times 32, right? So you'd have to have 32 pins to represent all those numbers. So you'd have 2,100,000,000 times 32, which, yeah, whatever, 64 billion. Anyway, different lines. So clearly not scalable. So what I wanted to do is apply some really easy math to determine which LEDs need to be on and which ones need to be off, and I wanted to show that off to you guys. So like I said, my difference here is I'm getting a random number, and then I am using that random number to do a small little calculation to determine which LEDs need to be on and which ones need to be off. And this code would really only scale with sort of one for one, sort of linearly, based on additional bits added. So if we wanted to represent a 32-bit number, we would need 32 unique lines versus whatever I said, 64 billion. And so here's how it works. So in our main routine, we're defining our pins. So we have a ones pin, a twos pin, a 4 pin, and an 8 pin, and these are associated with the pins that represent those numbers. So you have your 1s, your 2s, your 4s, and your 8s place. And then we go into a loop. And in this loop, we say generate a random number between 0 and 15. And let's tell the user that that number was selected. And then let's use that random number to calculate which pins need to be lit up. And this calculate binary state function here is just a custom little function I wrote to try and keep this main routine sort of clean. So I'll hop up and show you that here in a second. But after those are calculated, we sleep for 5 seconds to give us time to actually look at our output to check that it's right. So to show you the calculation here, just real quick, we're taking in the random number as a parameter and then the 4 different pins. And we'll actually use the 4 different pins as parameters to kick them on and kick them off. So here's our calculate binary state. So given a number between 0 and 15 and 4 pins, we toggle the indicator pins on and off to represent the number as a binary value. So first thing we do is we kick all of our LEDs off, just in case they pass in some illegal number, so a number less than 0 or greater than 15, our LEDs will be off and we won't be representing our old number. And then if the number isn't between 0 and 15, we let the user know that they passed in a number that can't be represented on our LEDs, and then we exit our function by returning nothing. And then next, assuming that we have a valid number, because this was passed, we define a dictionary of our LED values. And all this dictionary is doing is it's creating an association between the actual integer that is represented by the pin. So in this instance, the number 8 is represented by the 8's pin. So we know in our math down here, if 8 can go into our number, we should kick this 8's pin on. So it's just kind of creating a little mapping so that we know which pin to kick on when we get to it. So then we hop down here, and what we're doing is we're taking our random number that we passed in. So it could be anything, 12 or whatever this next one is, 2. Whatever that number is, when it gets passed into this function, we're setting this current value as that number. So let's say that current value was set as 13. 13 was our chosen random number. What we're going to do is we're going to loop through all of these different items in this dictionary, and we're going to do some easy math. So the number is 13. This current value number is 13, but the first number in our dictionary is 8. And so we say, okay, if the current value, which is 13, is greater than or equal to 8, then we know that 8 can be subtracted from it. So we kick that pin on because we know that that pin will make up at least a portion of the total number. And then we subtract our 8 from 13. And we assign the value of that subtraction back to this current value variable. So in this instance, 13 minus 8 assigned back to here is 5. Okay, so now we go on to 4's pin. So we have 5. Is 5 greater than or equal to 4? It is. So the 4's pin is going to be kicked on. And then we subtract 4 from 5, gives us 1. Hop back up. So this new value is 1. Now we're on to the 2's pin. So is 1 greater than or equal to 2? No, it's not. So that pin stays off, and we go on to the next one. So is 1 greater than or equal to 1? Well, yes, it's equal to. So we kick that pin on, we subtract 1 from 1, gives us 0, and then we're done with our loop. We would be done with our loop anyway because we ran out of values in this dictionary, but in case, say, the random number was 8, as soon as the 8 is reached, which is the very first item in our LED values, so it would say, is 8 greater than or equal to 8? Yes. Then we kick the 8 pin on. This would be 8 minus 8. It would be 0. Well, we know that none of the other pins need to be on because if any other pin is on, that means that it's representing another number that's on. And since we're already at 0, we don't need any more numbers represented. And so we have this little line here that says, if this current value is 0 already, let's just break out of this loop and exit our function. And that is perhaps my overcomplicated version of the homework assignment for understanding and using binary numbers. Thanks, guys.